Swayam Prabha. Digital India. Educated India.
We are talking about the one-dimensional problem, and there's another one-dimensional problem which is typically that appear in mechanical engineering is the string problem. So this is one-dimensional problem, and so here the string is taut, and then the loading is laterally loaded. So what we mean here is that we have a string here, like this one, between two supports here. So let us say a length of L, and okay. So the taut string, what we mean by is that the string which is not really L, slightly smaller than L, and then it is slightly stretched, so that it is fixed at the two ends. So that means that as such, the string is under tension to a value of T. So the string is under tension given by a force Ft here, and typically it is loaded by a distributed force Q. Q is the intensity of load per unit length. So under this loading, so what will happen here is that so it is going to undergo a certain deformation. So let us call this as the deformation here. Deformation, or you can call it as deflection, and which is given by W. W here, W is you call it as deformation or deflection. More common term is W, which is a function of X. So it's a one-dimensional problem, and the deflection is only a function of X, right? And it, typically, to tell some other data, the cross-sectional area of the string is A, and it is under tension G, and total length is L. So our task is to find out or derive a governing equation for W as a form of differential equation. Let us see. The thing here is that now typically I draw a diagram here showing that obviously the deflection is downward here. That's what we expect. But to be more precise, to be in tune with the positive convention. So the upward is positive convention, positive, and in the sense that a force which is acting in the upward direction is denoted by a positive quantity. So similarly, the deflection W is given by upward as positive. So let us, under that convention, so what we do is that governing equation or the equilibrium equation so if you want to so if this is the original x, and as I say, the upward is taken to be positive. Let's assume that this is the typical deformation, of course exaggerated, because all these things are supposed to be very small deflections. So here we have a deflection here of W here, and this is a distance of delta x, and this is delta W. And what else? The forces acting here are a T here and another T here. So T is acting in the tangential direction for the string, and you can also observe that the slope of the string is changing from point to point. And in fact, if you call this as this deflection, the slope is theta, and here it is theta, and here it is theta plus delta theta. Okay, so the slope is changing by a small quantity, delta theta. So this is the slope, and we know the slope is related to the actual deflection. So theta is given by dw by dx. Okay, so the derivative of w will give you the slope theta. Now let us also show the other force here. So we have Q here, which is so we'll show a uniformly distributed load over that small domain delta W, delta X, a Q there. So now let's look at the equilibrium of this elemental string in the vertical direction. So equilibrium of force equilibrium in vertical direction. In fact, you also try to recall this deflection is W is upward taken to be positive. Okay, so in the upward, so if you are putting all the force components in the vertical direction upward positive, so there's a T here which is downward here, and this T is upward, and the component of this T here is minus T, and then this is theta here. We'll put it as sine theta. Now at this moment theta is small. Of course, I'm going to make that simplification very soon. So T and the vertical component is sine theta, and so similarly here that one is T multiplied by this is sine theta plus delta theta, and that's the upward part. And then there's other force component here, Q times delta X. So Q is the intensity of the force, and multiplied by the length. So intensity of the force per unit length. So that is the force per unit length. So that is the typical units of Q, and we multiply by delta x so to get the total force here. Okay, so this is what is the total thing, and so you can simplify this. So you can cancel this first term. So what also we'll do at this moment, right now, instead of prolonging the steps here, so this theta being very small, so sine theta is typically equal to theta here, approximately equal to theta, and the same thing is true for that. And then you write this as theta, and you write this as theta plus delta theta, and you cancel the first term, and then you get t times delta theta, right, times q times delta x is 0, right? And then you can also write that t delta theta by delta x plus q is equal to 0. And then in the limit, so you have t d theta by dx plus q is equal to 0. Okay, so this is the governing equation of force equilibrium in the vertical direction. So here now we want to replace this theta in terms of W. So if theta is the slope, so which is given by dW by dx. So which now we'll write it as t times d square W by d dx of dW by dx plus q is equal to 0. So which finally comes down to so this is valid everywhere between x is equal to 0 to L. So this is the typical governing equation. Okay, so this is the governing equation, right? And what are the boundary conditions? So the problem is complete only when you talk about the boundary conditions also. So the boundary conditions are here. So what is that? So typically, so if this is the kind of application you have, so there is a string here, and then which is supported at the two ends, and so which means that at x is equal to 0, W is equal to 0, and at x is equal to L, W is again equal to 0. Okay, so this is the typical application of a one-dimensional string. Okay, so this is the governing equation followed by this one. Interestingly here, a offshoot of this application is a membrane problem. So what is a membrane problem? So we have a very quick application extension of this string problem is a membrane problem. So this is typically a tabla, so which is there. So at the end where people play with fingers, so that is nothing but made of some leather, which is really under tension. in all directions. So they tie the threads so that they pull it in the horizontal direction. So that means that this is a typical this is a flexible membrane typically made of some leather and then kept under tension. So in fact, this is T, which is there all around. Compared to this one-dimensional problem, here the T, we assume that it is distributed all around. Okay, so T is actually the force per unit length here, whereas in the earlier 1D problem, it is just the force. So I hope you can. So T is distributed all around the membrane. Okay, so this is how I drawn it like this. So that means that you can, this is a typical isometric view where the membrane is in the xy plane, whereas z is the vertical direction. So the plane of membrane is xy, and the lateral deflection or deformation is, once again, if you want it, in the form of W and so you can very clearly see that this has the complete resemblance of our 1D problem. The only difference here is that here the deflection, which is in the z direction, is a function of, say, there is a point P here anywhere, and this point P is going to have a lateral deflection depending upon the under the action of force under lateral loading. Under lateral loading. So it may be just the application of the load by the fingers, or it can even be anything else. In fact, it is actually it's a dynamic problem in the sense that it's not a steady state problem, and we can understand. In fact, the W will be a function of time also, x, y, and time. So those are the dynamic problems. But for the moment, for the steady state application, so if you have under the lateral load, so let us say following the same thing, Q, which is a function of xy. So it is just an additional variable y that's being written here in addition to the x. So is it possible now, if W is the deflection, which is a function of xy now, so earlier we wrote this one as T times d square W by dx square plus Q is equal to 0. So if W is a function of xy, so the same theory can be extended to 2D also. So then, so this equation here should consist of y also. So that means that that equation similar to 1D short string analysis. So what is that which we are going to write? So T times d square W by dx square. Now what we have is that another term d square W by dy square. So now W being function of two variables, we don't write d. So we'll write the partial differential dou. So we'll write dou square W by dou x square, dou y square. And now the other term q will remain as such. So instead of here q is function of variable x and y. Okay. So similarly w is also a function of x, y. So you can see that here. So this is a very nice problem. So in fact, you can also write it as this. So this is a very typical representation of the two-dimensional problem of a membrane, and d square W by dx square or dou square W by dou square plus dou square W by dou y square is equal to minus q by. So q may be constant or q may be a function of x, y, right? So this is now what we have is that what is the domain here? So the domain here, you can say if it is a circular domain. So the domain can be anything like this one. Or it can even be so the domain can be a circular domain as a typical tabla, or it can even be a rectangular domain, just like people jump up and down for entertainment. So for children, that's not, also is nothing but a membrane problem. Okay. So here the domain is typically any point P here is so xy is within the domain R here. If you think that R is the radius, so you can say that xy is within the circle. So or you can also say that x square y square is less than R. This is the domain. Whereas here you can also define the domain as what? X is varying between minus a to plus a, and y is going from minus b to plus b. So it depends upon the type of problem you have, and so this is we call it as domain. Usually we represent it by capital omega, and then we also have the boundary here. So what is the boundary condition? Just like we have done in 1D, so the boundary condition here so the boundary condition here, which is the boundary is gamma, which we represent by gamma here, is where W is equal to 0 on gamma. So this gamma can be, what is that? So it is simply root of x square plus y square is equal to R for circular region, or so for rectangular region you can also put it that x is equal to, or x is equal to E and or y is equal to B. This is for interesting, right? Okay. There is another seemingly unrelated application is in the domain of the torsion. So this now very nicely we discussed the 1D string problem and which we extended to 2D, and then the governing equation looked like this one. Okay, this is within the domain, right? And followed by the boundary conditions here. So this is usually called a Poisson's equation. This is called Poisson's equation. So we can even this is in fact this is because the right side is non-zero, so that's why we call it as a Poisson's equation. It is also possible in some cases that it is equal to 0, in which case it is called a Laplace equation. Okay, so if this is called so interestingly, so we have many typical applications in mechanical engineering. So where a particular problem falls under the class of Poisson's equation or Laplace equation. So what I was just trying to mention here is another very typical application in 2 dimensions of a typical this equation. So what I mean here, torsion. Torsion of a prismatic bar so this is if this is a circular cross section, so this is very well solved in our BTech programs. So where the twisting moment here is going to cause a twisting motion for this one by a certain angle, or it can also cause some amount of torsion stresses, which we know how to calculate. So tau, for example, is equal to given by T by J times R, right? Or MT by J into R. So this is very well done for circular cross sections, uniform circular cross sections. But if you have non-uniform, non-circular cross sections, in the sense that, so this is here, of course, it's all under various assumptions that circular cross-sectional planes will remain plane. But on the other hand, prismatic bar here so this kind of bars with non-circular cross sections, when subjected to these twisting moments, will have a little complex solution, in the sense that the cross sections here will not remain plane as it was here, which was true, whereas here cross sections remain. Cross sections will undergo will undergo warping. Okay, so we'll undergo warping, and then, so typically there is a theory developed by Saint Venant by a complex mathematical analysis of two-dimensional stress analysis. So here there is a warping function, or there is a stress function using in terms of stress function phi. So everything has been given here, and so it turns out to be that the stress function phi, which is a function of xy, is related to the domain. And then there are so many other things like so then there's a shear stresses here. XY as well as YZ here. And so this is now, we are supposed to solve this phi stress function, which is related to this kind of equilibrium or governing equation. If you compare this one with our earlier membrane problem, so this has exactly the same representation, right? So this, if you recall that this is exactly the same representation, you can also call this one as the Poisson's equation. Of course, here let me recall that G is the modulus and theta here is the angle of twist. Angle of twist, okay? So you can see that this problem surprisingly follows the same pattern of our earlier problems, right? So this is also a Poisson's equation. So if you know how to solve the Poisson's equation, you can solve really a host of problems of our typical mechanical engineering things. A similar thing you can also see in the case of, we are going to see in our next class about the heat conduction problem. So the heat conduction problem also has a very similar nature, and then there's so many other groundwater flows and so on. So they all fall under the class of this Poisson's equation or Laplace equation, okay? So what we have done in the class today is that we have derived the governing equation for some typical problems. We started off with 1D and then we have extended it to 2D for several problems of our interest. So we'll continue this one with application to heat conduction in our next class.